what I'm going to do is I'm going to go and look at the first area of our presentation. MasterSeries is a very wide-ranging program, and if I just start the software, MasterSeries 2020. So we have our frames, our portals, our connections, our retaining walls, masonry, pile caps, and all little standalone programs. I am going to work with a frame. That's the very old-fashioned column strip method, flat slab program that people have had in the past, which is being retired because of this new system. But before we do that, what I'll be looking at is bringing in a drawing from Revit, because we don't have to start from scratch in the MasterSeries. Now, I've only got an hour, so I'm going to be taking some little shortcuts from time to time. But if we look at a Revit model, it's got some shear walls, columns, openings, and it's even got columns that don't match upper and lower. So what I can do is I can go to Link Manager and I can create. So I'm going to remove the link, going to create a brand new link, and instead of calling it FE Slab, I'm going to call it FE Slab, and the time now is 13:05. Just so we know exactly that it's this one, and save that, and it's going to be a full model link, and I'm going to submit changes to, so it's sending those all out. I can then come along in here and go to import Revit link and connect to an existing link because we've already created it, and there it is, 13:05. Just open the file. And here we have the details, and we just say create new model from the link, and we're now asked what we want to bring in. I'm going to bring in slab elements, walls, and I'm just going to say extract and then load this file. So I can come in straight into the MasterSeries with a file, and here we go with our FE surfaces set up initially. But I'm going to step back a stage. And what I'm going to do is I'm going to come back and I'm going to create the first floor level for you. And I'm going to show you how we work with our fine element surfaces. So we've got first floor slab, some walls, and some openings. I'm going to show you how simple it is to create your slab and apply your loading on your slab. So, create, add surface. Very simply, and I can say give me the main border and say auto select main border. Now if I turn off 3D, you will see that in apply mode, when I pick that, it's going to try and do a column, but I can then come along here very quickly and do that. But that's a wee bit clumsy. What I can do instead is just pop this into elevation and just do that, and now I have my surface created. I can then run along and put in the openings and say yes, I have an opening, and auto pick an opening here. So I now have an opening in my slab. Very straightforward, very easy. We just define 4 members, 3 members, how many members you want to define whatever shape of opening you want, and just select that inside the slab. Edge supports, we don't have any. Attached beams, we're not going to put any in. Loading, we will have the basic dead load, and then we'll have an additional load which is going to be a live load. And because I want to do pattern loading to get the maximum sagging moments, I'm going to come along and say not live 1 but live alternate, and then I'll just put a value here on of say 5 or 6. So there we go, there's my surface created with its loading. Now material is the key item we're going to use, because we're going to do it, we're going to use a codified material, concrete, and it's going to be C2835. It's going to be 200 thick, And what I also want to do to allow for deflections is I want to allow it to use a cracked short-term load factor for serviceability loading cases. So that is as per the, I think it's the BRE Concrete Society guide on looking at FE analysis of slabs using elastic methods. So we are modifying in the service cases all of our Young's modulus, so we get a more realistic indication of what the deflections under the slab will be. And then we just repeat the same on the next side. Now I'm going to come out and I'm going to open the next slab. Try this one. Yeah, that's got it. So now we've got a progression here, and we have our two sets of floors all nice and neatly done on our 3D. The next stage we want to look at is loading patterns and loading cases. So if I look at my loads and loading cases, and I go to my loading cases, I will see I've got 12 loading cases. And I actually have loading cases with loads giving us spanning in one direction and then the other. And this will make more sense in a moment, because what I want to step back and look at is, very importantly under loads, alternate loading patterns. So what I've done is I've told it that this surface and this surface, let's look at just the top surface for a moment, or maybe the bottom surface. Let's go for the bottom surface. Level 1. I've said that I want this to be load group 1 and load group 1. So I have loads around here. And then this is load group 3. Sorry, I just clicked and jumped. So set 1 and set 2. If I look at the two together, we'll see that they give us a pattern, and that will allow us using L1 and L2 to go max min, and get me the maximum moments here and the maximum deflections in the mid spans here. But I also need to look at the opposite direction, so I also then created it perpendicular. Just turn those off. Load set 3, and you'll see we've now got the same style of pattern. It doesn't actually matter too much, the shapes, as long as you're looking at alternate panels. So this will give you the maximum here and the minimum there, max min, and then the vice versa. So those two together will allow me to play around and get those fixed. And you can see we've just had to create a wee dummy member in here, which is very easy to get me a path through there. It's a tiny couple of 100 mil gap, which just allows it to give me the valid patterns that I want. To do it with that all in yellow, and then this would cause problems with developing the maximum around here. This is more accurate doing it this way. So I have created my alternate load patterns. So between the alternate load patterns and the alternate load cases, we're now able to do our patterns. So let's look at those load cases. We saw the load cases, and loading case 1 is all spans loaded. Let's look what it means. It means that all the D1 and L1 values are 1 point or maximums. And then when we come to the alternates, we're adding max min. And then when we come to the next one, so that allows us to do the patterns in one direction, and then we repeat them in the other direction. And we also do the serviceability. In reality, you don't really need the serviceability with all spans loaded, because it's not going to give you the maximum deflections usually, but play safe just in case. So in this case we've got 12 loading cases. Very straightforward, very easy. So now we're going to analyze this. Very straightforward. We've done the preambles and we're getting to the real meat of our analysis. Static analysis. We've got a default mesh size. We've even got horizontal notional loads on the ultimate limit state, which is correct. We could even put wind loads on if we wanted to, but we're not going to. So space frame, off it goes, and quickly analyzes that. So far we've been using two programs, the master frame plus the finite element. That could be PowerPad plus finite elements, or it could be the building design suite with finite elements. One or other, it doesn't really matter. They will all work. And this will give us our analysis results. So first floor, second floor, a wee bit of interaction. Let's go back out to, well, you just click on the home button, you get full view. I'm going to turn off the mesh. We don't need to see the mesh outside the editor. And I'm now going to go into results and graphical results. And we will see that you get your bending moments in your columns, but we can go into shell elements and we can look at member forces, we can look at Y displacements. So we're going to see here under ultimate we're getting 13 mil max. Under serviceability we're now getting 34 mil. So less load, but it's a weaker cracked creep long medium term loading, and it's giving us 35 mil, which is probably okay for these sorts of spans. And if we then look at alternates, we'll see we actually get 32 here and we get 31 here. So in this case we weren't getting the maximums from that, but bear in mind we also then have the reversal of that when we have different patterns included. So we can do all of these and look at that. We can also come along and using primitive methods look at a rough area of steel, Eurocode, and it's going to give us top steel XX, top steel, and we can see that we're actually getting an idea here that probably 393 is going to be a good arrangement. Let's go for bottom steel, YY, and again looking at ultimate cases, all of them, we will see from our quick assessment that we'll probably go for 393, but over here we may need a slightly heavier, we may need to go up to 12s or even 16s for that sort of probably 16s in this area. So, and then in the opposite direction we can see that we're okay. Now that's just a general assessment. What we now want to look at is the finite elements design of the slabs, and I am going to take you into another file and we're going to see some things here that are very, very interesting. We're now moving into this new program, the concrete slab design. Somebody asked me, is it for flat slabs only? Well, you can have beams and have it one-way spanning if you want, but it certainly does use a finite element analysis method. So let's looking at this, come into design and concrete slab design, the new facility. Analyzing the frame. Just while it's doing that, somebody's asking about how does it work with cantilevers. Well, we've got a nasty little double cantilever over here where the column is pulled in from the side. Obviously we're going to have a partition rebate with glazing for his little balcony out here or something for the managing director of the organization. So here we go. It's just setting up the slab design checks. It's doing its own homework, and in we come. So let's look first of all at the final solution on the first floor, and then we will do the upper floor ourselves. So frame views, plan at level 1. What we've got is rebar, over supports, and general. And in general, in the T2 direction, which you can see is running that way and that way, is T10s at 200. And then we can see we have additional reinforcement over different strips of supports. We also have something over here which is a wee bit strange, but that's because that is on the bottom. We are looking at the moment in our top direction 2. And we can then look at bottom direction 1, and we can see over here the T10 basic is perfectly good, and over here we have got T12 basic plus additional 12s and additional 16s, because we actually have this transfer slab situation where we have this huge big column coming down, a single column which is then carried at the ground the first on 2 separate columns out here and here. So everything is all designed. So that's our reinforcement. If we want to step back to our unities, and we'll say draw the sagging maximum values, and because I have a new file, it's just forgotten that we don't really want the FE mesh. There we go. And so we're seeing in here we've got everything below 1. In here everything's good, and we can see that we're all happy. Now, if you decided then to look at this surface, you will see your values and your sagging. It's the hugging I'm interested in, and we will see our zones of reinforcement, and we can see a couple of zones that we need to reassess. That's all great and good, but what I'm going to do is to the roof. So let us start from the scratch on the roof. Let us change our frame view to roof plan, and let's start from scratch. Roof plan. Up to the top, I'm going to add in a basic reinforcement. I have none at the minute. I'm going to add in basic reinforcement and just turn that into a corner view. I'm going to add that to that slab. So that's now the slab I'm choosing. I could do the same over here, but I actually want to do them separate so that I can have 16s or 12s here separately. So I'm going to add in another group here, and again select and add that. And what I'm going to see is when I now go to plan and I scroll on down, I'm on a small screen here just to keep you guys not having massive bandwidth of video. I'm only in a 1200 by 900, which would be our minimum size. Usually you'll be working at 10 or 1200 deep rather than 900, or even higher on a 4K or 3K screen. So what I'm now going to ask for is on the selected slab, we can see where we've got our reinforcement hugging. We can see where our sagging reinforcement is failing. It's failing all the way down here and down part of this. So that's the X sagging. The Y sagging is also failing. So what we're seeing is a need to go above the 10s. So we're just going to resize this, coming down bottom steel. We're going to go from 10s to 12s, and from 10s to 12s. And we also have this beautiful little tool where we can actually see the unity for the both, and we'll see that we actually have still got these strips that are unhappy at 12s at 200. So I am going to suggest that we go up to 16s and 16s at 200, and then redraw, and we'll now find that we have no problems but 12s and refresh, we only have problems there. So yeah, I'm going to keep those 16s, and then over here I'm going to put those down to 12s and see it happens. Yeah, so both of them need to be 16s here because we only have a single slab here, so there's quite large spans in there. So That is the bottom steel there. The bottom steel over here, if I just scroll on up to set 3, which is this one, and ask it to redraw for it, you'll see that we don't have any problem except for a small problem in around here, and you'll probably find that that's quite small. So that's our bottom steel, and that's the steel we're not that worried about. Usually we've covered our basics, so we now have these basic reinforcements set out. What we now want to do is look at top steel. So let's go and looking in this area, come along, and we're going to look at hugging, and we'll just look at the hugging max in the selector. We can see all over here we have need for reinforcement. We can see that we're way up to 5-6 times our capacity. And yes, remember we have a wall along here, and we even have a wall along here, which is not really a big problem, but the wall along here is causing us to have hugging steel that we need to enact. So what I'm now going to do is go and put in some peak reinforcement. But before I do that, I want to go and look at my defaults, because this is where it gets fun. So 500, that's fine. Cover's fine. Cover, that's fine. Basic rebar we chose was that. Peak zones, we're going to go for 1 zone. We can go for 2 zone or 1 zone, and we'll see 2 zone maybe later on. But 1 zone I find is clearer. On the auto size resolution, I'm going to go for 250. So we're getting 1250, 1500, 17, 2 meters. You don't want anything simpler than that. We could go for 200 to match the steel, but it's easier just this way. And it will be additional steel. Strips, again, we'll be happy. On auto design, because I'm dealing with 200s as my basic, I don't really want to go for things like 175 and 150. That's going to get very complicated and very messy. To be honest, I would be happy not at 400s but at 100s if you need them, or 200s, and I wouldn't want them at 400. Well, no, we could take 400, of course we could, so every other span, and copy that down to the others. So that's my limiting rebars. Although that 100 is debatable whether you would like it or not, but let's try it anyway. So what we're going to do is we're going to add a peak zone, and we're going to tell it where we're going to put it. We're going to put it at the ends of columns only. So let's just take this one here. So here we've got our peak zone, and it's telling us the basic default additional of 10s at 200 again is not good enough. We've 10-15% overstress, and likewise. Now we need to possibly make it bigger. What I will do is I will ask it to auto size the size of the zone plus the steel required. And then I come down and I say auto do it. Off it goes, and it's now given me some rebars, but it's given me a little warning about strip averaging. It may be too big because we're taking a 2 meter width and it's averaged it over the full width. I recommend that we set it to be an effective depth limit, so it's only, in my case, I think the default's 5 effective depths, which we have found is a very good averaging value. We will redesign again, and we now end up with 10s at 100. So maybe I didn't like those 100s, as I was saying, because that's going to be an awful lot of footery steel. Let's go and take out the 100s and copy and save, and come back down here and say, right, let's go again. Auto design. We get 16s at 200 spaced apart. 10's at 100 or 16's at 200. 16's at 200 is easier to place. And there we go. We're interspacing the bars. And that's just in the one direction. In the other direction, we also actually need 16's at 200. And we'll see the whole thing is now working. Now, what we can now do is ask it to multiple add. And I'm just going to go all of those. And there they go. They're all been added. And if you choose any one, turn off the multiple, you'll see that one zone adds the basic over full width. So we would really want them all to be averaged, and we can just window to change all those in one go. So it was getting confused. And there we go. Now, these ones here, I would probably like them to be on this axis. So I'm just going to take this one and set the angle, say to 30. And that's the wrong direction, so I'm going to go minus 30. I'm going to go for this one very quickly, minus 30. And we're nearly finished, believe it or not, with most of our design. And I think I should be able to copy them and do them all in one go. Minus 30. No, copy doesn't. It should do, but minus 30. And this one, I will change it as well. It's quick enough, minus 30. And enter. So we can now say let's auto design. Coming down, and we can say all sets that are visible. Visible only, all sets. So that means all peak sets. And go. And it's now walking through down here at the bottom, doing the auto design. And we now have all varying, and I just go for a refresh, and Mr. Hugging all sets, or all, is probably easier. And there we go. Everything here is working. We've got a little bit of a transfer here with this other surface, which we're not looking at this moment in time. We may need to increase this one. And what we can do is increase that. But before we start dragging things around, it might be simple to tell it to work to the same resolution, 250, and at 30 degrees, so that we can actually work things quite easily. So looking at this, highlighting the rebar, I can extend that. So now we can see that everything is working perfectly fine. It's certainly more footery with the very low resolution, which is not what we recommend. Unity values, hugging, and off it goes, and it gives me everything is looking either blue or even coming down to the greens, except for this one here, which is not, needs to be resized. So down to peak, choose this one, and I can say, well, what I would really do for this one is I would tell it that it's not symmetrical. So there's the dimensions. So not square, but unsymmetrical. And then just take that down to there, that over to there. And it's now telling me that it should be fine. But it's telling me that I need just to extend it. That's better. So I can now fix that. Now, there's a little tiny problem around this opening, and I would prefer to see that just incorporating that opening more to give us better reinforcement. So that's all working except for, in this case, this one corner in here, which is a similar problem. And we actually just need to redesign that one. And it's just got a little problem with it. And that's better. There we go. Now, you'll notice we're getting all our dimensions, and we can come along because we've got everything nice and neat. We can say, well, actually, if that's 2.5 and that's 3, you know, let's make them both 3. So let's move out, zoom in 0.25 in both directions. And likewise, if that's 2.5, let's make this also 2.5. So let's keep everything the same size. And sometimes that's more useful from a practicality point of view. You can come back and rationalize everything. So last thing we need to look at here is this column strip here, or so this wall strip. And we can handle that using the third method, which is very straightforward, which is the strip method. So let's add in a new strip. And because it's a strip, it needs to know where. So I'm telling it this on this surface. And then I'm coming along and I'm going to draw from there to there. And it will be bars that are going to be perpendicular. So it's going to run the bars that way. An extra 10s and 5 effective depths. And we will just do a refresh, and everything is now okay. Extra 10s, doubling up the 10s over that support is going to tell us we're fine. And this is slightly more problematic. I can come along and add a strip and draw it along that line, but then everything's going to be measured either perpendicular or parallel to the line, which is out of plane. I don't want to do that. What I prefer to do in this situation is to come along and just draw. Oh, I have to tell it the slab first. There we go. Now I come along and say draw from here. Excuse that, I'll just redefine that. Draw from here. Strangely, it's okay. We can work with that. It's drawn it from there to there. I'm going to take this end and move it over to here. Take that end and move it over to there. So we're now vertical again. But what I'm also going to do is I can, for the strips, I can modify the start and ends. So I can turn around and say, well, actually, we just need that to go from there to there and from there to there. So as long as the two overall lengths are the same, then everything will be happy. And I am just going to go and do a refresh. And now it's all happy. So there are no failing components in this environment. So that's that slab done. Now we can come along and do the same over here. And to do that, we're going to go back to the peaks. And we'll just pop them in one at a time. Add multiple. I'm going to go one there, one there, one there, one there. So it's not. There we go. I need to be inside the slab just. And that's that done. We've already done all those. So now for these, I can now say auto size and see what we get. So if we turn off the add, come down here and say, let's just select that one, hold the control down, that one, that one, that one, that one, that one. And I can say all sets, selected sets, and it's now resized those with a wee bit of an overlap, and we will just use the larger of the two. We'll just let that stop short and refresh the graphics, and we're now seeing that we're getting everything fine. Now we are still getting this over here and here, so you might take the attitude of saying, well, let's just take that right out to there and have that over there, and we'll actually end up using this heavier reinforcement here rather than this, and that's us done. And over here we've got the tiniest of overlaps, and this is where the 30 degrees tracking is very useful. It allows us to draw these a lot more accurately. And this one appears to be slightly unhappy. We just need to put bigger rebar in. I'm going to put 12s in. And redraw that. So what is it the problem on this one is? So everything's all fine except for this one. I'll not spend time fixing that one yet today. So what I'm going to now do is look at the output for this. I'm going to look now at the rebars we've defined. So we can see our basic reinforcement. And we can see in each direction, bottom is only 10s and 16s, that's absolutely correct. Bottom direction 2 is the same. Top is where we get the fun and games. There we go, all sets. So now we're drawing the sets, and we can see in each direction what we've got. And bear in mind that the rebar here is going into different to here, so we will need a lapping bar between the two sets. And we can take that and export it. And as you saw earlier, if we're in peak modes, we can take these and we can rationalize their sizes. We can rationalize their required rebar to make everybody's life a lot easier on site. And possibly, I don't know if I needed 2.5 sticking out there. Maybe we could get away. Pulling that down to be nice and neat, and if we then checked back we can see whether or not that would work. But we can then send that straight out to AutoCAD, and we will do that in about 5 minutes time. In the meantime, the last thing that's required is the dreaded punching shear, and this is again fantastic. So let's just go back to our unities. And let's just now come up to punching shear. And we will see nothing's happening. What I need to do is to add a punching shear check here. And it's saying, no, we don't need any. The rebar's heavy enough. And we can add another one here. And again, it looks to be fine. And that's a bit strange, but we'll see why in a minute. What I'm going to do is I'm just to add them all in. There we go. Take off that, and let's look at any one that the punching shear is not required. There we go. On the inner ones now it is required, and we can see that we've chosen radial bars, I believe. What method did I choose? Equally spaced around the perimeter. I'm going to choose the more popular radial layout. So we can then take that and use shear rails to mimic that in our design or in our construction. So there we go, there's a simple now. What are these all about? That's a brilliant question. That's a wall, and really the edge of corners of walls are very overlooked with regard to punching shear, and the shearing stresses around here can be horrendous. So we do need to consider punching around this perimeter, and likewise around this corner we may need on the inside some punching checks, and likewise over here. We also need to look at this sort of arrangement. Now, we have modeled our columns external, and that gives us a slightly simpler FE analysis. It also gives us slightly longer spans, which is conservative. But when we're looking at our rebar and our rebar perimeters required, we are actually not taking it out to there. We are taking it the full rule out. We're assuming that the edge of the concrete is at the outer edge of the column, and we will then use the required perimeter for that, and we will use the Eurocode column edge perimeter and the outer perimeter rules, the U0 and the U1 values correctly for that. Only in here do we end up using it and ignoring the rest and just checking about this point as required in the code of practice. So the punching shear is very, very clever. And if we come up here, we'll see that this is a column that's circular and therefore requires either equally spaced or radial, but cannot do grids and cannot do cruciform. Cruciform is quite nice again. If I was to go back to one of the square piles internals that needs, there we go. And what we've seen here is that it's actually omitted, it's understood the opening close to the column, and has actually modified the column design to allow for the reduction. So the reduction of U1 from 3986 meters approximately to 3737. So it has curtailed the check perimeters correctly for the openings in the structure. But there we go. If I was here, I can come along and do equally spaced, which is horrible because the steel fixture is going to really love you. Radial we've seen. Even grid just means that they're set out on an even spacing of usually around the 200. 140s, you can see them 140, 140 and 90, 95 out from the column. Or you have this unusual one that's supported in the Eurocodes where you do the cruciform, where you just put them coming out 3 rails, 3 rails, 3 rails, 3 rails, and it does modify the perimeters to allow for the cruciform style of design. Now all the time we've been using the code method for calculating the required punching shear on this column head. The code method, or we can use the FE surfaces method, and the FE surfaces method, it does another check further on out and still gives us the same reinforcement. So the code knows what it's talking about, and again we have to do an averaging around that, but I'm going to go back to the code method. So this is my punching shear. So this column is underneath. If I jump to my original planet level 1, you'll remember I have these two columns underneath, and I then have this point load, in essence, coming down. So what I need to do is to check the punching around that column coming down and not continuing, and then obviously on the ones that are then resisting it further on out, carrying its own slab plus this dirty column load, and it's all done automatically. So that's all your design, your analysis, everything done. What we need to do finally is to either print our reports, or in my case I want to export, and I'm going to export the bottom two, and I'm going to export all information, and load AutoCAD. And we're going to go for 1:100 scale for our text, and we're going to go export. Off it goes. AutoCAD's loading on my other screen. I'll just pull it in as soon as it's finished loading. And this will give you all the information you need for your detailers. Here we go. And what we've got is don't need that. Oh, sorry. What we've got is we've got 4 views. 1, 2, 3, 4. So we've got bottom in the direction 1, and it actually shows you the direction of the rebar, and then the bottom in the next, and it tells you over here that you're using this reinforcement, and then in here, and we've done 2 strips. We've done an middle strip and an outer strip for the rebar in this instance. And then you come up to the top steel, and you can see the top steel set out for you, and you'll see the strips here designated for you. And then you have the same in this instance for yourself, and you can then just take those and do the full detailing. Very straightforward, very simple to use. So that is how simple it is to design your slabs. Somebody asked about piled slabs. Piled slabs are done in the same way. The only difference is that you can't do the peak and punching shear unless you have a column underneath. So I would always recommend it that the column is placed underneath each pile location. Interestingly, if these were piles and I didn't want to do the reinforcement at, say, this one, it's this one we're looking at. If I didn't want to do the shear reinforcement, I can come along, and I just have to scroll up a wee bit and say, well, quite frequently in piles on rafts, or not rafts, piled floors, suspended floors, you'll come along and create a localized drop. So I'm going to create a 250 drop all round. I'm going to make it 100 mil. And now what we're being told is it's not big enough. Outside the drop is not good. Inside the drop we're fine. So the 100 mil extra is fine to work without shear reinforcement. We just need a larger drop. So let's make this 500. Alright. So a 500 drop of 100 mil for extra in the base is perfectly good, and all you need to do to resist the punching shear. So in the piles on a floating slab, you can create a localized meter square or thereabouts piled area, if you know what size your column is, then you could work that out more accurately. Let me see. Design. What size is the column? Support face. And I'm not seeing, I don't know what size the column is, in fact. That's probably a 400 by 400 or something like that. So if it's a 400 by 400, you might turn around and say, well, we'll make the drop 1500 square, and so 600 all round or thereabouts, 550 all round. So that would give you 550 of a projection. So it's 1500 all round for your drop, and that would now prove that you don't need any shear reinforcement. So ladies, gentlemen, thank you all very much for attending today. If you want any prices, just email me at sales@masterseries.com or just direct to myself, help@masterseries.com. Any technical questions, obviously into help. And if you want to try the software, just register online using the free trial request. If you're an existing user and want to try the FE Slab Design, just again get in contact and we will get you all sorted out. So ladies, gentlemen, everybody, thank you all very, very, very much for attending today, and have a great day and stay safe.